Hi and welcome to the Multi-Agent Learning course. Today we're going to discuss gradient ascent. The idea of gradient ascent is that every opponent is identified, so is set equal to possibly mixed strategy. So perhaps you observe the opponent's actions and translate these observations into a possibly mixed strategy. You can observe that possibly mixed strategy of your opponent, and after observation, the idea of gradient ascent is that every player changes his strategy a tiny bit into the right direction, and the right direction is of course best reply. So you don't give exactly best replies in fictitious play. Also in fictitious play, opponents are modeled through a mixed strategy, but they play best response to it. But gradient ascent, players know their mixed strategy of their opponent, and they, as a response, they move a tiny bit into they change their own mixed strategy by adapting it a tiny bit into the right direction. So in gradient ascent, players do not project a mixed strategy, they actually know the mixed strategy of their opponent. And they do not play a best response, but move a tiny bit into the direction of a best response. So we'll first discuss two-player, two-action general sum games with real payoffs, and discuss the dynamics of mixed strategy in such games, familiar games. Then I will discuss infinitesimal gradient ascent as proposed by Singh, Kearns and Mansour in 2000, discuss convergence results, and then I will discuss IGA WoLF, win or learn fast, as proposed by Bowling and Veloso, and discuss convergence properties. So we'll first discuss the general framework of 2x2 games. So in its most general form, a two-player, two-action game in normal form with real valued payoffs can be represented by a matrix top, bottom and left, right for the column player, and top bottom for the row player, with lowercase r payoffs for the row player and lowercase c payoffs for the column player. We represent mixed strategies by alpha and beta. Alpha is the probability that top is played, and 1 minus alpha is the probability that bottom is played. Beta is the probability that left is played, and so on. So you can, with this information and these payoffs and these mixed strategies, you can actually compute, as you already know, the expected payoff. So the expected payoff for player 1, which is the row player, is, well, the probability that he plays left times the probability that the column player plays left, plus the probability that the column player plays right times the payoff which is obtained for the row player in that occasion, and so on. So this is just the formula that you already know to compute the expected payoff in case payoffs and mixed strategies are known. And we abbreviate this formula by letting U be we have terms for alpha beta, we have terms for alpha, and we have terms for beta, for beta, and we have rest terms, remainder. So this term is too long to write down, so we abbreviate it. I'll give the abbreviation in a moment. So similarly for the payoffs of the second player, if mixed strategies alpha and beta are known and the U and U prime, so here's U prime, is abbreviated like so. You see this, those are constants. So these are constants. These are not occasional abbreviations because the U and U prime, this is U prime, will return very frequently in the remainder of this presentation. So they are very important. So the first player wants to move his strategy into the right direction, and he can do this by computing the partial derivative with respect to the only parameter the first player has influence on, which is alpha, his own mixed strategy. Alpha determines his own mixed strategy. And if you compute the partial derivative of the payoff of the first player, you will end up with this expression, which of course depends on the mixed strategy of the opponent. If it doesn't make sense to you now, please bear with me, because I will repeat this idea in various guises. So if you combine those two partial derivatives, you will obtain a so-called affine map, which is a linear mapping, a matrix applied to a vector of mixed strategies plus a constant vector, and you can abbreviate this very nicely into this expression. So just as to get things neatly organized. So you should think of the parameter space alpha beta as represented in a unit square, where alpha varies among the x-axis and beta varies among the y-axis. So in the origin, alpha and beta are 0, and in the unit square we have various values of alpha and beta, and in particular there might be one value where the derivatives are 0, and the derivatives are 0 if you set those two equations to 0, and then you have a so-called stationary point, which is where there is no movement. There is no incentive for both of the players to change their strategy, so that's actually a weak Nash equilibrium. As you can see, because two linear equations only give one solution, so there is at most one stationary point. Well, there is always one stationary point, but it may lay outside the unit square. No, there is at most one, because sometimes a stationary point does not exist, because this set of equations does have solutions. But if it exists, it may lie outside the unit square. And if it's inside the unit square, it is necessarily a weak Nash equilibrium. So let's consider an example in Stag Hunt. So we have a reward payoff for both parties of 4, a temptation payoff of both parties of 3, a sucker payoff for both parties of 1, and a punishment payoff for both parties of 3. That's just common terminology: reward, temptation, sucker, and punishment. So we have two players. Player 1 represents red, and he may vary his strategy along this axis here, the front axis. And this payoff surface depends, of course, on the mixed strategy of the opponent, which may vary his payoff among from back to front. And so which is the red surface? So a combination of mixed strategy alpha, for example, alpha is 0.6 and beta is 0.2. Then we're here, and the payoff for the first player here is on the red surface is somewhere here. And the payoff of the second player is somewhere here. So the first player has only the possibility to move from left to right, and the second player, which has the blue payoff surface, has only the possibility from back to front. So you see, if both players want to move here, well, the row player wants to move to the right here, and the column player wants to move to the back. So this is a stable and pure Nash equilibrium here. And also here, the row player, which is the player with the red payoff surface, wants to move to the left, and the column player, which is the player who is able to move from front to back, will move to the front with the blue surface, and we have the other equilibrium where both parties cooperate. No, defect. So there's the probability 0 here to cooperate, so the probability to defect is 1. And here at the back right here, the other pure Nash equilibrium, both parties want to cooperate because the probability to cooperate is 1 here for both parties. So these are the two stable pure equilibria, and here's the weak mixed Nash equilibrium where both parties cooperate with let's say 60%. And this is a weak equilibrium because if one of the parties doesn't change strategy, then for the other party it can reply with either response because it doesn't change the payoff. You see this line is horizontal and the blue line is horizontal as well if the first player doesn't change. So this is the stationary point. Here both players won't move. This is not a stationary point here. The two pure Nash equilibria are not stationary points because they want to move outside the unit square. So the unit square is the surface on the ground. They want to move outside the unit square, so that's not a stationary point. And here as well, though both players want to move out of the unit square, but they get stuck into the corner. Here players really don't want to move, so this is a stationary point. The weak equilibrium. So we first discuss, so this is the same equation. So alpha is the mixed strategy of the row player and beta is the mixed strategy of the column player. And the idea is that both players each round, so in the next round, alpha beta in the next round is alpha beta in the current round, plus a tiny bit of adaptation into the right direction. This is the right direction for the row player, this is the right direction for the column player. So because the mixed strategies are in the unit square, the dynamics must be confined to the unit square. Now I already explained that the mixed strategy pair is on the boundary of the unit square and the gradient points outwards, then they can't improve further. So that was the case with the two stable strategies in the stack hunt game, which I showed you earlier on. So to maintain dynamics, well, I could just as well show. So if you stack hunt, and you see here, well, the payoffs are not the same, so I should use the payoffs, what is it? Here, which is 4313, 4313. 4, 3, and 1, I believe. So here we are. So reward is 4, temptation is 3, soccer is 1, and punishment, if both defect, is 3. And we have the dynamics like so. And you see that here's the weak equilibrium. Here, there's no movement. Here, in the right upper there is this pure equilibrium. And there is movement, but the movement is stuck into the corner. And here you see the other stable equilibrium. So if both parties has a tendency to cooperate, they will fully cooperate if they adapt. And if both parties has a tendency not to cooperate, they will fully defect in the end. So you see this is the same picture as this one. So this describes the movement and this describes the payoff surfaces. Sorry for flipping back and front, this may be confusing. So if you're stuck in the corners, then one of the players has an incentive to move but cannot improve, so he will not improve. And if non-zero, the projected gradient is parallel to the closest boundary of the unit square, which you can see here. You see? Here the movement is parallel to the boundary. Okay, back to the slides. So this is the very same equation. It's not a different equation, but the same equation. The affine differential map is written in full. Just to show that this map is the central point of the discussion and quite important. So there's a theorem of Singh, Kearns and Mansour, only from 2000, which is quite recently, that says if players follow infinitesimal gradient ascent, where eta is going to 0, then their average payoffs will converge to the expected payoffs of some Nash equilibrium. And if the strategies converge, may or may not happen, then those strategies will converge to that same Nash equilibrium. And the proof is based on results in mathematics that says, well, there are a couple of cases. The main matrix capital U is invertible, so you can compute the inverse matrix, and its eigenvalue, which is by definition the solution of this equation, which is the determinant of capital U minus lambda, where lambda is a variable, which is the eigenvalue, minus the identity matrix is 0. If the solution lambda is real, then there is a stationary point, which is a saddle point. And if the eigenvalue is imaginary, because the solution of a quadratic equation, for example, lambda to the lambda square plus 16, then you only have imaginary solutions. Then there is also a stationary point, but that is a centric point, not a saddle point. And third case, if the main matrix U, capital U, is not invertible, then which is equivalent to either one or both of the lowercase u and u prime is 0, there is no stationary point. So this is a saddle point. You see there's an optimum in one direction and a minimum in the other direction. That's called a saddle point. So let's go through a couple of examples to see what goes on and how you compute the eigenvalue. So here's the coordination game. It's a symmetric game, it's not a zero-sum game. If you compute the gradient, so just fill out the affine map formula, you will get the gradient in the unit square here, and the gradient of the coordination game. So so the coordination game means if both parties tend to coordinate, they will fully coordinate, and if both parties tend to coordinate, so here the first player barely wants to coordinate, but the second player desperately wants to coordinate here, then both players will not coordinate. They will be attracted to this point, you see. So in the gradient is the formula for each point in the xi plane or in the alpha beta plane, which is the same, that dictates to which direction the arrow points. So the gradient here is the vector points in the direction of 2 times y minus 1, 2 times x minus 1. So here it points in no direction because 2 times a half is 1, minus 1 is 0. So here we have a stationary point. And here the vector points into the direction, well, the y is 1, so it's 2 times 1 is 2, minus 1 is 1, so the x direction is 1. and the y direction is 2 times x is 2 times 1. Sorry, the x direction is 2 times y, that is 2 times a half, because we are at the half here. So the x direction is 0, and the y direction is 2 times 1 minus 1 is 1, so the vector is 0.1 and points into the north, back. So stationary point a half. The U matrix is looks like this, and we compute the eigenvalue by putting minus lambda here. So and we compute the determinant, which is minus lambda times minus lambda minus 2 times 2. So minus lambda times minus lambda, which is of course lambda square, minus the other diagonal, minus 2 times 2 is lambda square, minus 4 is 0. We have real eigenvalues, so we have a saddle point inside the unit square. The same for the prisoner dilemma. We compute the gradient with the affine map. The gradient is nowhere stationary in the unit square, because the stationary point lies outside the unit square. There's real eigenvalues, so well, it's not interesting here because there's a movement everywhere, and the movement at all points is towards the defection. The probability to cooperate is 0. The probability to play the first action is 0, and so on. We have a couple of examples which you can sort out. Sterkund, Game of Chicken, Battle of the Sexes. Matching pennies, which is a particularly interesting example because the first player wants to coordinate and the second player wants to anti-coordinate. We have a stationary point a half, but this matrix has imaginary eigenvalues because here lambda or negative lambda times minus lambda is lambda square, minus 4 times 4 is minus 16, so this is lambda square plus 16, so it's imaginary eigenvalues. And we have then, due to the result of Singh, Kearns and Mansour, a stationary point inside the unit square, which is the center of the dynamics. So here there's no convergence. You see, if you're here, then there will be no, sorry for flipping, there will be no convergence. So if you take matching pennies and you are here somewhere, then both parties will never converge. Other game with imaginary eigenvalues. So here the movement is elliptic and not in the center of the unit square. So just to show that the station point doesn't have to be the center of the, and the movement is counterclockwise as opposed to the other example, which matching pennies, the movement is clockwise. Okay. So convergence of infinitesimal gradient ascent. There are just a case distinction. Well, the first case, if there's no stationary point or the stationary point lies outside the unit square, then there's movement everywhere in the unit square, like for example in the prisoner dilemma. And its movement is caused by an affine differential map. The flow is in one direction then, and the flow then gets stuck somewhere at the boundary. So that at that point there's convergence, because simply the movements get stuck there. Well, the second case, there is a stationary point and it's inside the unit square. Then we have two subcases. That stationary point is an attractor. Then it attracts its movement and become stationary, but actually that never happens with 2x2 games. But the other case happens. Well, both cases don't happen. A and B do not happen. So you won't have an exclusive attractor and you won't have an exclusive repeller, but you can often have the combination of the two. For example, Battle of the Sexes and Chicken Game, you have both two, A and B, and then you will have a saddle point. However, these are not all the cases, because the stationary point is neither an attractor nor a repeller nor the combination of both two, a saddle point. And then we have strategies that do not converge. So this is the case with matching pennies, for example. The stationary point lies inside the unit square, and the eigenvalues are imaginary. So in most cases there is convergence, but in this case there is not. Now the idea of WoLF is to invent a solution to ensure convergence for this remainder case. So let's move on to IGA WoLF. IGA means Infinitesimal Gradient Ascent, with the idea to adapt the dynamics, win or learn fast. So if you do not win, then you will increase the gradient with a certain factor, and if you do win, then you will not increase your learning with a certain factor, but we will discuss that. So here it is. They temper with the learning rate. There's a learning rate for the first player, L sub 1, at every round 2. So the learning rate varies among rounds for player 1, and there is a learning rate for player 2, which varies among rounds. And the learning rate is chosen from L min and L max, and it doesn't matter much what those values are. Let L min, for example, be 0.9 and L max be 1.1. That's okay. In the article of Bowling and Veloso, this is represented as an interval, but it is a typo. So you really have to choose from two learning rates, L min and L max. L min is smaller than 1, L max is larger than 1. Then the idea is to define the learning rate for a certain player. Well, without loss of generality, we choose for the first player that the first player choose the slow learning rate if his payoffs at that point is larger than the payoff at that point where the mixed strategy of your opponent is remain equal, but he replaces his mixed strategy by the mixed strategy of a Nash equilibrium, any Nash equilibrium. So this is called winning. So if his payoff is larger than the payoff in the combination of its own Nash equilibrium and the similar and the same mixed strategy of the opponent, that's called winning. And learn fast otherwise. So if you're not winning, if you're losing, then learn fast. Same for the opponent. So alpha E is a row strategy belonging to some Nash equilibrium chosen by the row player. Similarly for the column player. And these might be other Nash equilibria. So the Nash equilibria chosen by the column player may be another Nash equilibrium. So the combination of those two mixed strategies may not be Nash. Now, In any case, however you choose the learning rates for the first player and the second player, the trajectory of the strategy per alpha beta is an elliptic orbit around this point with the axis that depend on the learning rate and the learning and u and u prime. So there are 4 possibilities depending on u and u prime and whether this expression ultimately is larger or less than 1. The elliptic orbit lies flat and has axis smaller than 1, stands as axis smaller than 1, lies flat as axis larger than 1, and stands axis larger than 1. They have enumerated all possibilities. Now that is a result proven elsewhere. Now there's a... So we're still busy with making up a solution for this case in which there is no convergence, to enforce convergence. So we need the following result: the player is winning if and only if that player's strategy is moving away from the center. So this lemma effectively says that winning is moving outwards. So when play revolves around the center, then there can be only one equilibrium, which is the weak equilibrium. So the chosen alpha E and beta E are in fact that only one weak equilibrium, and that is in fact an equilibrium. Now we have defined that the player wins if this is the case. Now we consider the case only for the row player, and this is the case. Now if we solve this and we isolate the dynamics and this one, we end up with this equation which says that the product of those two expressions must be 0. So if a product of those two, so this is the other expression plus the, so must be positive. So that means both are negative. So this one and the fraction, the partial derivative, must be negative, or both must be positive. So both are positive, so the mixed strategy of the first player lies to the right of alpha E, and alpha increases, so it moves away to the right side, or the mixed strategy of the first player lies on the left of alpha E, and the first player moves indeed to the left. So indeed, a player is winning if and only if that player's strategy is moving away from the center. Okay. So that means that at any one quadrant relative to the chosen equilibrium, which can only be the weak equilibrium, the learning rate is constant, because players are either constantly and consistently to the left or right, or upper or lower for the column player, upper or lower for the column player to beta E. So only when players pass the boundary of the quadrants, the learning rates will change. Now towards the proof that learning will converge only also in the last case. So if C is the center of learning, so alpha star B star, then for every initial strategy pair alpha beta that is sufficiently close to that center, the win-or-learn fast dynamics will bring that strategy pair eventually to C. So if you have such a strategy pair, then its trajectory will form an ellipse with center C. Well, if the strategy pair is sufficiently close to C, then there's no interaction with the boundaries of the unit square. So the boundaries of the unit square do not play a role anymore in the dynamics of the trajectory. So the trajectory will not be disrupted. Now there are two cases. The strategy pair moves clockwise, and we thus have to ensure that the parameters are set such that the ellipse that forms the trajectory stands when alpha beta is in the odd quadrants and lies flat when the strategy pair is in the even quadrants. And if the strategy pair moves clockwise, then we'll have to execute a similar reasoning. So let's just make a drawing. So here the movement is clockwise, and we have to make sure that the ellipse lies flat when we are in the second or fourth quadrant, and the ellipse stands when we are in the third. We are here in the third and in the first quadrant. So, well, because if that's the case, so it lies flat if the movement is in the second quadrant. If that's the case, then there's convergence, you see? And you see that the learning rates remains constant. No, the learning rates do not remain constant because alpha and beta change, but the learning factors L1 and L2 remain constant. Until a boundary is passed of the quadrants, and then the shape of the trajectory changes here into a flat ellipse. And in this case there will be convergence. So in words, the learning parameters Lmin and Lmax alternate in such a way that the ellipse that forms the trajectory in clockwise movement lies flat when alpha beta is in the odd quadrants and stands otherwise. So now suppose the movement is clockwise in the drawing we just saw. Then the alpha beta pair is in the upper right of the ellipse. Then rho moves outwards, so wins, and col loses. So rho moves slow and col moves fast. That means that the horizontal velocity is smaller than the vertical velocity and the ellipse stands. And similarly, if the strategy pair is in the second quadrant, the ellipse must lie flat. And there clearly the reasoning is similar if the strategy pair alpha beta is in the other two quadrants. Or when the movement is counterclockwise, it's the same reasoning. So this proves the claim. So that's all there is to it. So basically when you have this picture in mind and you understand that the learning rates are made such that the form of the trajectory is adapted such that the movement is going spirals into the origin, then it's okay. So I proposed another solution. So why not utilize the result on empirical frequencies that in all cases the empirical frequencies converge to the empirical frequencies of a Nash equilibrium, converge to a Nash equilibrium. So why not use that So this is the result, which I repeat. So this we already discussed, and we use this one. At least their average payoffs will converge to the expected payoff in Nash equilibrium. Well, then yes, use these average payoffs to correct the gradient. So the gradient points slightly more into the direction of the average payoffs, and then you'll get convergence without win or learn fast with adaptation of the gradient. So let's do that. So let's correct, and we have matching pennies. Then we will have convergence. Like so. You see? Well, you get the idea. So thanks for watching, and hope to see you on the other side.